and beyond. So the malate-aspartate system lets us get electrons into the mitochondria so they can be used to make ATP. It's really cool and it involves this amino acid aspartate. So let's talk about how it works. So ATP is basically how our bodies store energy. So much more on this in another post, but basically it has these 3 phosphate groups which are negatively charged. So it's kind of like holding them together is kind of like, I like to think of it as kind of like clamping a spring, like a tight spring. And so if you break one of these phosphate bonds, then it's kind of like if you unclamp the spring, and just like how it might like fly out something, if you had something on the end, it would like fly out. Well, it's kind of like that's because of the energy. And so it's kind of like you're releasing energy that you can then use to do other things. And you can store it by like controlling when you are releasing this energy, then you can use that energy instead of like to flying something off the end of a spring to do things like helping make unfavorable reactions favorable. And so we can have these reactions happen. And so in order to do this, our cell needs to be able to make ATP from a lot of different things so that we have it like when we can take anything we eat, we can take something with sugar, with something with fat, protein, whatever, and break it down, generate ATP, this universal currency that we can use for all sorts of different things. And so there are a bunch of different metabolic pathways that can do this. Some metabolisms like the making and breaking of molecules. And so catabolism is where breaking things down. And so a common place where things start is like if you start with glucose or like blood sugar. So from 1 molecule of glucose, you can end up getting around like 30 or so molecules of ATP. But you can't just take a glucose and be like, voila, we have ATP. Instead, you have to go through a lot of different steps to get there. But the good thing about this is that you have all these different steps. You can take things along the way, like break down products and use them to actually build things. So a lot of times you're not just like going straight to the ATP, you're actually using intermediates to go build things. So like anabolic stuff. But anyway, so in order to get the ATP out of the sugar, you go through glycolysis, you go through this like citric acid cycle, and then you go through oxidative phosphorylation, which is where this big payout is going to come from. So you're getting ATP along the way through these various pathways, but you can see like glycolysis, that part you only get like 2 ATP. Citric acid cycle, again, you're only getting 2 ATP. But then you come to oxidative phosphorylation, and here's your big payout. But it's the reason why we're able to get all this out of oxidative phosphorylation is because we're taking electrons that we've transferred throughout this process and turned them into these carrier molecules like NADH and FADH2. These are going to transfer electrons into that we can use in oxidative phosphorylation. And it's these electrons that we're actually going to be using to drive the ATP making. And how this is going to happen is that through this thing called the electron transport chain. What this electron transport chain is going to do is it's going to pump out protons into this inner membrane space. This is going to cause a high concentration of protons, which is going to be used to kind of like drive this pump, kind of like a water, like a dam, where you have a high concentration of protons, and you're going to be pumping them out in multiple places. So you can pump a lot of them out with the energy from those electron transfers, but you're only giving them one way back in. And this way back in is going to be this like a lot of protons is going to help drive, like kind of turn this motor. This ATP is going to actually make ATP. So this oxidative phosphorylation, it's relying on this oxidation and reduction or redox. So basically, oxidation is loss of electrons and reduction is gain of electrons. So much more on this on another post, but often, but not always, oxidation is accompanied by a gain of bonds to oxygen or a loss of bonds to hydrogen. And reduction is often, but not always, accompanied by an increase in bonds to hydrogen and a decrease in decrease in bonds to oxygen. And so much more on that in the other post, and I'm not really going to go into it here.
But for now, just know that oxidation is loss of electrons, reduction is gain of electrons, and we are going to pass the electrons from one molecule to another in the electron transport chain using the and we're going to pass it from something that wants the electron, doesn't want the electron that much, to something that wants it more, to something that wants it more, to something that wants it more, to something that wants it more. And by doing this, every time we pass it to something that wants it more, we're releasing a little bit of energy, because we're making it happy. When you make molecules happier, you release energy, basically. You can think of it kind of like as you're being uncomfy and you're kind of like wiggling around, and then you're more comfy. And so you're using less energy, you're not like wiggling around. So you've used that, you've released energy. And this energy is being used to pump out these protons. So as we go down this pathway, we're going to be transferring the electrons from something with a lower reduction potential to something with a higher reduction potential. So basically, we're passing it to something that wants it more, to something that wants it more, to something that wants it more, and then ultimately you're passing it to oxygen once it wants it really, really, really bad. And so this is how we get this system to keep running. And then this is all that energy that you're releasing, each of those transfers is being used to pump out the protons. And then the gradient, you have a high concentration of protons, which is then going to flow back in and turn this molecular motor to make ATP. And then you have ATP you can use. But in order to do that, we need to have these electron carriers. So we need to get the electrons onto those molecules that want the electrons, but they're also willing to give them up. And so a couple of the key ones that we see in biochemistry are FAD and NAD plus. And so basically it's kind of what they're going to, so we're going to be looking mostly at NAD plus and NADH. Note that there's also NADPH and NADP plus and NADPH, which are often used for like anabolic stuff, so like building other things. So it can be kind of hard to see, but what's happening is that when you are like reducing NAD plus, what's actually happening is you're having a hydride transfer. So instead, we're having a hydrogen is transferring with its electrons. So we're not having a proton transfer. We're not just like having when we talk about like a proton transfer, when something gets protonated, what's happening is that the hydrogen is being transferred without its electron. So it's just a proton. When you have a hydride transfer, what's actually happening is you're having a hydrogen that's transferring with electrons. And so since it's transferring with electrons, what it's actually going to do is it's going to be reducing the thing that is transferring through. And so in this NADH, you have this positive charge on this nitrogen. What's actually going to happen is it's going to help, you're going to have this like electrons moving through this ring. So you can see this is where we're going to get a new bond to hydrogen. And what's going to happen is this is going to happen, and this is going to like push the electrons. You can push them around and put them on that nitrogen. That's going to make the nitrogen happier. And you have reduced this compound. Once you reduce it, everything's reversible, right? So now you can oxidize it. And when you oxidize it, that's when you're going to be releasing those electrons that can be used to help pump this system and get it going. So in order to make energy from the electrons that we're generating throughout all these various steps of the pathway, we can put those electrons onto NAD plus or FADH. And then those can be used in this in the electron transport chain to generate ATP. But this is happening. In order for this to happen, we need this NADH with the FADH2. We need this to be in the mitochondrial matrix. Your mitochondria is like this cell-bound compartment inside of your cell. So basically, the glycolysis and stuff is taking place in just like the general interior of the cell, the cytoplasm. But then the rest of stuff, most of the other stuff, is going to take place in the mitochondria. So in the mitochondria, it has these two membranes. And so this is going to have, you're going to have this like mitochondrial matrix, so this inner part, then an inner membrane space, and then you have the outer mitochondrial membrane. And so the inner membrane, you have is where the electron transport stuff's going to happen. The matrix, so the inside is where the citric acid cycle stuff's going to happen. And then the inner membrane space is where the protons are going to be pumped in from. So we're generating we're going to be generating a bunch of electrons and stuff inside of the mitochondrial matrix, because that's where the citric acid cycle and stuff is going to happen. So we have glycolysis happening in the cytoplasm, then we have this inner membrane space, and then we have this mitochondrial matrix, which is where we're going to have the citric acid cycle happening. This is also where the ATP making is going to happen. So most of the electron carriers we're going to make through this respiration are actually going to be made in the mitochondrial matrix, because that's where the citric acid cycle and all that's happening. But glycolysis is happening in the cytoplasm. And with glycolysis, we're generating 2-NADH. And so we need to be able to get this into this NADH into the mitochondria so that it can be used to like power this stuff. We really, really want to get that NADH in, because for each NADH that goes in, you get about 10 protons pumped out. It takes 4 protons coming in for 1 ATP to be made. So 10 divided by 4 is 2.5, so you get about 2.5 ATP per NADH. So we really want to get that NADH in, but NADH can't get in. The problem is that this mitochondrial matrix, this inner mitochondrial membrane is super duper selective. So this outer membrane isn't quite so selective, but this inner guy is really picky about what it lets in. In fact, this membrane, so even though it's like a lipid membrane, it's actually like 80% protein. So there's like a bunch of proteins. And so there are carriers for various things. But there aren't carriers for getting NADH in. But there's a workaround. And this is where the malate-aspartate shuttle is going to come in. And so when you're making the NADH in here, the TCA and all of that, all's fine. But when you're making it in glycolysis, now we've got to get that NADH in. We can't get that NADH in, but that's okay, because what we care about from the NADH isn't the NADH itself, it's those electrons. So if we can transfer those electrons to something that can get into the inner mitochondria, then we're good, right? We don't need to worry about letting NADH itself in. And so we actually have NADH inside of there already. So we have like NAD plus in there that we can transfer those electrons to if we get it into the inner mitochondria, so into the matrix. But we just need to be able to pass those electrons, get the electrons in here that then we can use to make NADH that can then be used in the pathway. So in order to do this, we're going to pass it through in the form of these malate. So these two transporters that we're going to talk about are the glutamate aspartate antiporter and the malate alpha ketoglutarate antiporter. And so antiporters, basically that means that they're letting one thing out in exchange for letting something else out. So with the glutamate aspartate antiporter, we're letting in glutamate, taking out aspartate. With the malate alpha ketoglutarate antiporter, we're letting in malate and we're letting out alpha ketoglutarate. So basically we can take oxaloacetate, which we can get from aspartate. It's also a product, it's also one of the intermediates in like the citric acid cycle and stuff. So this is a common molecule. Now we can use this enzyme malate dehydrogenase to basically take NADH, and we're going to take the electron from NADH and we're going to use them to reduce malate. So remember, oxidation so is loss of electrons, reduction is gain of electrons. So we are reducing malate, which means, and we're oxidizing NADH. So basically we're taking the electrons from NADH and putting them onto malate. And we're doing this, you can see that this is you're getting the oxidation here, where this carbon now has only a single bond to oxygen instead of two. And so it has a bond to hydrogen. So it's fulfilling both of those basic, like often but not always, this is accompanied, reduction is accompanied by loss of bonds to oxygen and or gain of bonds to hydrogen. And so now you have this malate molecule. This malate molecule can go through this malate alpha cube glutarate antiporter. So this malate is going to come in. When this malate comes in, however, you're going to let alpha ketoglutarate out. But as we see, we want to let it out because it's going to help us cycle this all through. So the malate comes in. And now what's going to happen is the malate has those electrons. And now we need to get those electrons back into NADH. So we need to add those electrons to NAD+. And when we do that, now we're taking malate back to oxaloacetate. And it's using the same enzyme. So enzymes can basically, they're speeding up reactions, but they speed them up equally in both directions. So out here, you have a bunch of oxaloacetate and a bunch of NADH. So this enzyme, the reaction is going to be driven this way. So if you have more of this reaction can go either way, but you have a bunch of more of this stuff. So it's going to go primarily this way because you have all of this stuff and not much of this stuff. And so now you're going to go this way. You're going to make this NADH or this NAD plus and the malate. So the NAD plus is going to stay out here, and it can be this can be like regenerated and stuff. But this malate is going to come back in. Come in, and so the malate comes in exchange for the alpha ketoglutarate. Now, when it comes in, you have the same enzyme in here in the like a mitochondrial malate dehydrogenase. And it's going to do the reverse reaction because now you have a bunch of NAD plus, you have a bunch of malate. And so you're going to reduce NAD plus and you are going to generate oxaloacetate. So you've oxidized malate, you've reduced NAD plus, and now you can take that NAD plus to electrons through the electron transport chain to make ATP. But now we need to recycle everything so that we can do this again. So now we have oxaloacetate in here. Oxaloacetate and the oxaloacetate, we don't really want in here. We don't really need it. So like, let's get it out, right? But we can't get it out directly. So we're going to transfer it to something that can get let out. And we're going to do this with the help of an aspartate aminotransferase. What this is going to do is it's basically going to take this amino group from the amino acid glutamate, and it's going to pass this amino group, it's going to pass its amino group onto oxaloacetate. And when it does this, when you take oxaloacetate and you add an amino group from glutamate, you're going to get aspartate, the amino acid aspartate. When you do this, this aspartate can leave in exchange for another glutamate coming in, so you can redo this process when you generate another oxaloacetate. When you remove the amino group from glutamate, you get a molecule called alpha ketoglutarate. This alpha ketoglutarate is what we exchange in order to get another malate in. So we are now cycling all of this stuff through. So you can see that we have the malate. We let the malate in, and we let the alpha ketoglutarate we just made out. So we're letting out the trash in order to, and then like letting in the fresh stuff. So we're letting out aspartate, which can be used out here to make glutamate from alpha ketoglutarate. And that alpha ketoglutarate is what we just made when we took the glutamate and we took oxaloacetate and we made alpha ketoglutarate and we let that out. So we're letting out the stuff we're making, and we're letting in the stuff we need to make the stuff we just made and let out. And in the process, the only thing that's like really the whole point of all of this is that we're moving these electrons from the NAD plus, so from the NADH through malate. We're going to do. So this is like the really, really crucial part. This stuff. This is all we need to regenerate everything we just made. We need to regenerate all those carriers. But the key thing is this malate that's going to carry those electrons in. And so it's just this one carbon that's getting like getting reduced out here, oxidized in here. And this is producing the NADH that we need. And it's really just remaking the NADH that we had out here, but now it's making it in here, which is where you have the electron transport chain going on. And so this is why we need the NADH in here, because it's kind of useless to us out here, at least for the purposes of making ATP. This malate-aspartate shuttle system is the main mechanism of getting NADH into the mitochondrial matrix in the liver, heart, and kidneys. Some other tissues use different ways. Just a quick couple final notes on aspartate, since it is the amino acid of the day in my 20 days of amino acids. So it's the 16th day. We're getting there, people. So you might sometimes see it called aspartic acid. So basically it has this carboxylic acid group in our bodies. So we talked more about pKa's yesterday, but basically a pKa is a measure of like an acid's strength. So if you're above the pKa, you're more likely to be deprotonated. Aspartic acid, so the carboxylic acid form, has a pKa of around 3.7. This is well below bodily pH of about, this is well above the bodily pH of about like 7.4. And so we're about 4 pH units above its pKa, which means that only about 0.01% of it's going to be protonated. So you have very little actual in the aspartic acid part, and it's almost all in this aspartate form. And so the aspartate is the deprotonated form, but you'll sometimes see this referred to as aspartic acid. So basically it's the same thing. People often use the terms interchangeably, although technically this would be the difference. Yeah, and it still has the 3-letter initial, or 3-letter, its nickname is ASP, which makes sense. Its initial is D, which makes a little less sense, except that A is taken by alanine. And so with D, you can remember it's kind of like aspartate. But don't use that trick if you are then if it makes you spell it wrong. But so the 2 acidic amino acids, so the ones that have these carboxylic acid groups that can in their side chains that can get deprotonated, there's aspartate and glutamate. And so aspartate is going to be D and glutamate is going to be E. So if you remember that these 2 are D and E, then you can remember either that A comes first, so it's a D, and D comes before E, and A comes before G, and D comes before E, or you can remember like aspartate. But basically these are just a couple you're kind of gonna have to remember that they're weird. And as a fun historical note, so it was first discovered by the hydrolysis of another amino acid, asparagine, which we'll talk about tomorrow, which got its name from asparagus, and that's why it has that name. But when they found it, they weren't sure that it was, they didn't know if asparagine was a protein letter. And so when they were naming aspartic acid, he chose aspartic in this Plisson in 1827. He chose aspartic instead of asparagic to emphasize that they didn't know if it was really a natural thing. So they didn't want people to confuse aspartate for being a natural product of asparagine, which we now know that it is.